Hello and welcome to Lecture 15 on the topic of exoplanets. As we continue our lectures in astronomy, we've moved out of our own solar system and now we're considering other solar systems. Now, it hasn't been that long since scientists have actually known that there are such a thing as other solar systems. Of course, we've long suspected it, but only modern scientific techniques have confirmed the existence of planets around other stars. And that's what we mean when we say an exoplanet. It's outside of our solar system. Okay? So, to talk about that, we want to talk a bit about the model of the solar system, which we've talked about in the context specifically of our solar system, but how it might apply to others. Then we'll talk about some similarities and irregularities with a solar system like ours. Then we'll talk about the techniques for searching for extrasolar planets. How do scientists actually find them? And there's a few neat ways that are discovered. Then we'll talk about what we know so far about the trends. What types of planets are being discovered around other stars? Then we'll talk about the closest exoplanets, some of the special types of exoplanets, and dwell on the question, is our solar system unusual? Which has a typically unsatisfying scientific answer, but certainly one that encourages further study. Okay, so let's take a look. So, modeling planet formation. Where do planets come from? Well, we now have many planetary systems other than our own to test, which is crucial because when you only have one subject, it's hard to get good results. So we can really test theories about formation and see how much they hold up. Now, as of 2013, there were 900 confirmed exoplanets and about 2,500 candidates. As of 2021, we have about 5,000 confirmed exoplanets. Okay? So we have lots and lots of these discoveries being made. So many new exoplanets are being discovered on a regular basis because there are so many stars in a few light year distance of our own star. Okay? So let's talk about the theory about where planets come from. And in that model, that theory of planet formation, the key word here is condensation. This is like the same word that we'd use for water condensing on a surface. But here we have matter condensing into planets. So we have a very large interstellar cloud. All right, this is how a star is born. It is a cloud of gas. Okay, it's going to be molecular hydrogen that's mixed with dust. It's able then to continue to cool and collapse under the influence of gravity. As it contracts, however, it heats up again. Okay, but it's still able to continue collapsing under the influence of gravity. Okay, and that's key because without particular elements in that cloud, they never collapse in the first place. But once the cloud becomes molecular hydrogen, has key molecules like carbon monoxide that allow it to actually release radiation, it collapses, and it collapses to a tiny fraction of its original size. Because we can see here, we're going to zoom in on a much smaller space than the original cloud. About 1/100th the volume of the cloud will become the solar system. So then in the very center of that very collapsed cloud, a sun is formed. Eventually fusion begins inside of that star, and then we actually have a star system born. However, there's much dust left over, and that dust provides condensation nuclei, so that's this condensation centers, around which planets can be created. So essentially the remaining dust around what's going to become the star, right? Because here we can see the star, that remaining dust begins to clump together. And as the clumps become larger, the larger clumps, like a snowball rolling downhill, pick up more of the smaller clumps. And thus we have a solar system of dust becoming a solar system of just a few planets. Okay, becomes a state like our own solar system. And yes, there's some remnants like the asteroid belt and the Kuiper belt full of comets. Yes, indeed, remnants, right? Or even trapped moons around the large planets. But mostly our solar system has condensed into just a few planets. Okay, as they grow like that snowball, they sweep up smaller debris around them. Okay, and indeed, this ability to sweep up the debris within an orbit is our current definition of a planet, which separates it from Pluto, because Pluto has not swept up all the debris in its own orbit, which is why it's now classified as a dwarf planet and not an official planet, which is why we only have 8 planets in our solar system. All right, and indeed, our example here is our own solar system. All right, and this takes about 100 million years, as we can see here, for really the planets to form. Obviously, for the planets to have surfaces that could support life that would take a few hundred additional years. Our own planet, after only 100 million years, was molten, and we think life didn't start until later. Okay, so this idea of condensation theory is great and it's a wonderful theory, but there's some behavior that it doesn't explain. Okay, now it does explain the broad strokes of planets being formed and is a important framework, but we have a lot of examples within our own solar system that don't quite fit condensation theory. And let's talk about those exceptions. So we're going to go over them. Exception number one, Venus. Venus seems like it actually might have been two separate planets. That would explain its lack of a magnetic field. That would explain the fact that it's spinning in the opposite direction. So very, very unusual case here, and it may have been two large bodies, two maybe Mars-sized planets that at one point formed Venus. Another strange exception is the Earth-Moon system, our own Earth and Moon, because the Moon is much larger than it should be, considering the size of our terrestrial world. None of the other terrestrial worlds, Mercury, Venus, or Mars, have moons anywhere close to the size of our Moon, and so that suspects that there's something unusual there. And indeed, we think that it may have formed from a giant collision, knocking off a big piece of the upper surface of our own planet. Our planet then re-solidified on its surface, and then the Moon condensed into its own spherical current state. But there's more. All right, we have a late collision that may have caused Mars's north-south asymmetry, okay? The different poles, for example, and stripped away most of its atmosphere because Mars has a surprisingly tenuous atmosphere, which means there's very little. All right, so that's another interesting case. Uranus, right? Uranus is tipped about 90 degrees on its side. That may have been caused by a glancing collision, because a glancing collision then could result into those particular dynamics. Glancing means rather than a head-on collision where the energy would have just been delivered to the core of the planet, instead maybe a Pluto or larger size planetoid swept across the surface of the gas giant. Miranda, a moon, may have been almost destroyed in a collision, which is why we see it broken up into such huge chunks, right? So it almost really looks almost like a sci-fi example of the whole planet blowing up, but then gravity pulled all those big pieces back together, and now the planet looks like just a tumble of huge chunks, which is quite amazing. Number 6, interactions between the Jovian protoplanets. Okay, so these are the Jovian planets before they became full size and fully formed. And planetismals could have been responsible for some of the irregular moons we see. All right, so irregular moons with strange orbits, orbits that go in the wrong direction, like Triton going in the wrong direction around Neptune. So, that definitely could be an example of that. And we also have interactions between Kuiper Belt objects, and particularly binary Kuiper Belt objects like Pluto-Charon, that could have been formed through collisions, because dynamics don't support an actual a two planetary system like Pluto and Charon, because essentially they orbit each other. They orbit a center of mass between them, because Pluto is not much smaller than its own moon. And it doesn't seem like that could have formed on its own. And so the theory is that there has to be some sort of interaction, like a collision, to bring those planetismals together. And planetesimal means just a small forming planet. At this point, we call one a dwarf planet, Pluto, of course, and we call the other its moon. Okay? And Pluto is slightly more massive, so I guess it's a fair designation. But notice what all of these exceptions have in common. They're all linked by the idea that it was a catastrophic, or at least near catastrophic collision at some critical time, maybe in those first couple 100 million years, that led to this unusual phenomenon that we now observe today. Right? And today being some 3.5 billion years later, the system being much more fully formed, we can assume all those dramatic events are in our past. Well, we'd hope so. Okay, so that's not ideal from a scientific point of view, because normally scientists, right, do not want to explain things by one-time events, because you can always say, oh, well, this amazing thing must have happened to explain it. The planet must have bounced off the other planet, and then, but that becomes very unlikely, and science drives and seeks to have the most likely explanations for what we observe. However, there is something to back up all of these one-time events, because it certainly is clear that there would have been a lot of opportunities for interactions and nearly constant collisions in those first 100 million years, because the solar system was so much more crowded. There were so many half-formed planets, so many more planetismals, dozens more than exist today. There wasn't 8, there was 30 maybe. And so that process, that bouncing in and then one collision leading to another, and so that period of a few million years of collisions is more probable in this particular context. It's just so unlike what the solar system looks like today. Okay? And perhaps we'll never know for sure, but we can certainly continue to study all of these exosolar planets, these planets on other star systems that may be in the early stages of formation themselves, and get a window into what our own past may have been like. Okay, so that is hopefully a good segue to talking about the search for extrasolar planets. Okay, so how do scientists discover exosolar planets? Because stars are really far away. We've talked about how the stars are so far away that ancient astronomers thought that they must have been fixed in place, or that perhaps Earth was fixed in place, because they don't appear to move at all, despite the necessary concept of parallax, that we are orbiting in a 150 million radius circle around our own star. Well, that's because the nearest star is over 3 light years away. So we're talking trillions of kilometers away, incredible distances. How do you see a planet at trillions of kilometers? We can hardly see Pluto in our own solar system, which is just a few billion kilometers, right? In fact, a factor of 1,000 or 10,000 less than the nearest star. Well, we have to use some pretty clever techniques. And they're mostly, these exosolar planets are discovered indirectly. So we aren't getting these photos of these exosolar planets. And if we could get a photo, the exosolar planet would just take up a pixel or so, even in the best camera. But we can definitely observe their behavior, their gravitational tug on their star. Because if we consider Jupiter, for example, Jupiter tugs on our sun, and it causes the sun to wobble back and forth. If an observer, like an alien in another solar system, was to look at our sun, they would notice that wobble, and they'd be able to calculate the mass of Jupiter from that wobble. And that's exactly what Earth scientists do. They observe these wobbling stars. And they also observe variations in the brightness of the stars as planets pass in front of them. And that's what this indirect observation of exosolar planets is all about. Okay, so let's talk about a few of the distinct techniques. So one big thing is many planets around other stars have been detected because they're large enough to cause that wobble, a pull back and forth, okay? Because as the planet and the star orbit around their common center of mass, the star moves. Because yes, the star is much more massive than the planet. Even in our own solar system, Jupiter being the biggest planet, it's still much less massive than the sun, right? More than one, or less than 1,000th the mass of the sun. So then how much wobble is there? Well, not a lot, but enough. Because we have in this dramatic example, we could assume a center of mass that is way outside of a star. So maybe a very, very large planet, like a planet that is 5 or 6 times bigger than Jupiter, orbiting around this star and maybe orbiting much closer. So it's really pulling on the star because the center of mass is right there. So you have one point when the planet is up here, and then the balance point. 'Cause think of this like a teeter-totter, right? The planet and the star are balancing, and this is the fulcrum, the balance point, right? But then when the planet moves to the other side, the star has to move to the other side as well because they have to remain balanced. That's what a center mass is all about. And solar systems are these steady systems that have balanced themselves out over time, right? Through that accretion, through that condensation of matter into the planets, the balance was naturally formed. And then the balance often means that the star wobbles, okay? So here in this case, if you were viewing the star from this direction, you would see it up and down wobble. So you'd actually see the star move back and forth. Now, this would be a very small back and forth optical wobble because it would only take up a few fractions of an arc second. So it would probably be less than 1/10 of an arc second. So you'd have to have a very good optical telescope to actually see that little bit of light moving back and forth. But that does happen, and there are some planets that we detect through this optical wobble. However, there's another type of wobble that's actually easier to detect because it has to do with the Doppler effect. And so we don't need to actually see the star moving back and forth. We just have to see it shift color. And it turns out that that color shifting is much more sensitive to motion than the actual back and forth wobble. And so if the wobble is instead transverse, then to our line of sight, then we can detect it through the Doppler shift. Okay, so I want to make sure I explain those ideas because this right here would be a perpendicular wobble, right? So it's perpendicular to our motion, but a transverse wobble would be back and forth, right? So if the observer is here, right, here's the eye, the wobble then is towards us and away from us. So we can't see that in an optical sense because the star is not moving up and down or side to side. But since the star is moving away and towards us, colors of light from known elements, very well-known elements like hydrogen and helium, well, those elemental colors have very particular known wavelengths in the laboratory. So when we look at a star and we know that that star contains those elements, we can look at those particular fingerprints, those elemental fingerprints. But when we look at these wobbling stars, we see that the colors don't match the laboratory, that they get either shifted in the red direction, which means that the star is moving away from us, all right? Or they get shifted in the blue direction, which means that the star is moving towards us. And based on the shift of the measured wavelength, we can directly relate the shift to the current velocity of the star. And so we see then that the motion of the star is this nice sinusoidal motion, which just represents the periodic wobble of the star as, of course, the planet periodically orbits the star. Okay, and those velocities come on the order of 10 to 100 meters per second. So they're not particularly fast, especially by astronomical speed standards, right? Just a few dozen meters per second is not all that fast. But again, the precision of measuring wavelengths allow for such relatively small velocities to be measured very accurately. Let me zoom in on this a bit, okay? Here's an example of a wobble, an actual wobble in a star system known as 51 Pegasi. This is a confirmed extrasolar planet. And we can see it's really creating a pretty significant wobble because in our own solar system, this blue line right here would represent the magnitude of the wobble caused by Jupiter. So obviously this planet is either much bigger than Jupiter or much closer to its star than Jupiter because it's causing a bigger wobble than Jupiter would of our own sun. Okay, and again, that'd be as measured by aliens in another star system. They would see a wobble that would look like this would be Jupiter, see much more flat. Okay. And there are other much more complicated examples, like in Upsilon Andromedae, where we have multiple planets all showing up in this overlapping pattern. So astronomers can look at this overlapping pattern of orbits and actually then determine that this is maybe caused by 3 separate planets, and then break through by analyzing the different data, seeing what is the orbital period of each planet. Okay. All right, and here is here's like basically the wobble that happens in our own solar system due to the planets, Earth, Mars, and so on, orbiting around the sun. Okay, all right, so that's the idea of measuring the Doppler effect of transverse motion of stars. Okay, gravitational periodic tugging on a star due to an extrasolar planet. Okay, but another good way to discover extrasolar planets is a reduction in brightness. Okay, so they can be detected when they lie in the plane of our vision to our view to that star, because when they eclipse the star, they reduce its brightness just a little bit. They decrease its luminosity. And we can measure that change in luminosity. And again, this is a thing that scientists can measure very accurately because they can measure just small variations in energy, just a few less watts per square meter. And they can say, well, the star is steady otherwise. There's no explanation to explain variable fusion rates inside the star. And if it happens at a steady rate, say, every 10 days, then that's a planet orbiting around that star every 10 days. And what's important about this technique, this idea of measuring small reductions in the luminosity of the star due to an eclipsing planet, is it can be used in combination with like the transverse wobble to allow for good independent confirmation of the planet. Because if you have it both wobbling gravitationally and luminosity decreasing because of the eclipsing, then that's strong evidence pointing to a planet. And that's what confirmed planets are all about, where we have more than one measurement, or at least one particularly good measurement. Okay? So certainly we see the idea here, intensity, that's that luminosity being completely flat, but then when the star gets eclipsed by a planet, it reduces a little bit. And that reduction is usually on the order of about 1/100% of the luminosity of the star. And that's on the high end. Sometimes it's 1,000th of a percent or a 10,000th of 1% of the luminosity. So these aren't large decreases in luminosity, but they are measurable. Okay? Okay, so those are the primary techniques, so definitely ones we want to focus on. There's more that astronomers can gather, including they can actually look at when the planet goes behind the star, so the opposite of the eclipse, when the star actually blocks the planet, that actually also causes a reduction in light, because normally the planet is there to reflect some of the sun's light. So when the planet goes behind the star, there's a tiny reduction in light. But what's great about that reduction is that reduction can sometimes correspond to particular elements that would only exist in the atmosphere of the planet, that is then its view is being obstructed as it goes behind the star from our point of view. And that's amazing, because then we can actually start to look at what that planet's atmosphere is made out of. Now, of course, that requires incredibly accurate measurements, the type of incredibly accurate measurements that need to be done by a space-based telescope. And there are space-based telescopes doing this type of work, but it'll just continue to have to get refined in terms of the actual data being collected. Okay? But continuing with the more than 900, all right, extrasolar planets have been discovered, and the 2,700 candidates, of course, that number being higher now, there are some interesting trends. And you might think, oh, well, maybe this is just going to be boring, and I'm going to tell you that, yeah, it turns out that all other solar systems are just like ours. No, they're not. The other solar systems we've discovered so far actually don't look much like ours. But there may be some good reasons for that, either because our solar system really is unusual, or maybe we're just not good at finding solar systems like ours, or at least not good at finding planets that are common in our solar system. So let me explain what that is or what I mean over the next few slides. Okay, so most of the planets we found so far are cold Jupiters, which is like Jupiter. Okay, now why would I call that a cold Jupiter? Well, you'll see, because I'm going to talk about something called a hot Jupiter in just a minute. And we also saw plenty of cold Neptunes, and that's like our Neptune, because our Neptune in our own solar system is definitely a cold Neptune. Again, that name is going to suggest that there's going to be such a thing as a hot Neptune, and indeed there is. Okay, and that categorization of cold Jupiters and cold Neptunes is due to their size, because Jupiter size would be a Jupiter size, we call that a Jupiter planet, and a Neptune sized planet, we call that a Neptune type planet. And the distance denotes the cold. Because as we know, as you move out into a solar system, as you move farther and farther away from a star, like in our own solar system, as you move farther and farther away from the sun, things get colder and colder. You pass the frost line, you pass that line where comets have no tails, because comets only grow tails when they come interior of the frost line. And you also pass that line where Jovian planets can exist, because then you can have those hydrogen compounds that allow for Jovian planets to exist. Inside the frost line, there's only asteroids and terrestrial planets, and comets with tails. Okay, which basically means a comet boiling off, that isn't going to last forever. But that's the idea. All solar systems have that division. That division between the terrestrial, interior of the frost line section, and then the Jovian outside of the frost line section. That it isn't always the same distance for each star, because different stars make the frost line move closer or further away depending on how much energy that star outputs. But the point being is that all solar systems have that division. Okay. Okay, now, another interesting thing about what we've discovered so far, we've discovered so far that the general trend of orbits, are smaller than the orbit of Jupiter. So mostly we're finding planets interior of Jupiter, okay? And they mostly have high eccentricity. Now that's surprising, because in our own solar system, most of the planets have low eccentricity. Eccentricity means elliptical versus circular. So if you have an eccentricity close to zero, then you have close to, so an eccentricity close to zero means you have a circle. So if your eccentricity equals zero, that's a circle. And many of the orbits of planets in our own solar system are nearly circular. Earth's own orbit is nearly circular. There are some like the comets and even Neptune that are more elliptical. Mercury is surprisingly eccentric, which means it's more elliptical. But when we look at other solar systems, lots of highly elliptical orbits, so high eccentricity. So as eccentricity gets larger and larger, as it approaches, it doesn't get infinitely large, but as it approaches, 1 and 2 and, gets larger, then you have elliptical orbits, which we call eccentric orbits, okay? All right, which means really stretched out. So this would be like a circular orbit, and this is a very eccentric elliptical orbit, okay? So we can plot the data. We can plot those confirmed extrasolar planets, okay? So let's consider one of those plots. So the upper plot shows masses and orbital semi-major axes, think of it like a radius, for hundreds of known extrasolar planets, with Jupiter, Neptune, and Earth for comparison. So let me zoom in over here so we can take a look at this graph. So on the vertical axis is planetary mass, okay? So planetary mass on this axis. On the horizontal axis is semi-major axis, like radius, okay? So we can see Earth is right here, okay? So Earth is in a section where we would have a distance from a star. We see that this corresponds to a cold region, depending on the star, all right? But a region that is not in a not particularly hot, okay? Not like Mercury hot, obviously. Then we have Jupiter, right, with its distance from our sun, right? And this is measured in astronomical units. Of course, one astronomical unit is exactly Earth's average distance from the star, from our sun. And then we go all the way out to Neptune, which is the very edge of our solar system, some 15 well, actually about closer to 20 astronomical units from the sun, okay? And then we can see on this side, when we look at planets' masses, we can group together these giant planets, which are probably failed stars, brown dwarfs. We can see that Jupiter really isn't that close to being a failed star. It's not nearly a massive enough Jovian planet to be a brown dwarf. But we found plenty of gas planets in other solar systems that are bigger than Jupiter, all right? And we found a lot of planets that are basically just like Jupiter, right? We found planets that are the same distance and the same size as Jupiter. And we determined the size based on the gravitational wobble. That's how we know the mass of these extrasolar planets. So Jupiter seems to be a very typical planet. Neptune, we actually haven't found any planets like Neptune. Wonder why that is. And look, we actually haven't found many. We found a few, and more recently in the last few years, but very few Earth-like planets. Huh. And then we got some categories that don't really match up with planets in our solar system. Because look, there's a lot of Jupiter-sized planets that have orbits that are less than 1/10 of an astronomical unit. That's really close. That's closer than Mercury is to our own sun. But yet we have giant gas planets that are that distance. That seems to fly in the face of our understanding the frost line. Because we talked about the fact that Jovian planets have to be formed outside of the frost line because otherwise there's not enough of that gas in order to create a big enough gravitational pull to pull in more gas and get that feedback loop of forming a gas giant, a Jovian planet. All right, that's why there's no Jovian planets mixed in with the terrestrial planets in our own solar system. But yet we see them in other solar systems. Is our data bad? No, we don't think so. We really think there are lots of these hot Jupiters. It's not the last time you'll see this term, but that's very unusual. That's not something we saw. Okay? Then furthermore, we can collect even more data in the lower plot, because the lower plot shows planetary radii and orbital semi-major actions for thousands of candidates, right? So we can group together even more, and we see that the trend holds up. We have lots of large planets relatively close to their stars. We also have lots of large planets up to about Jupiter's distance, but nothing going all the way up to Neptune, and nothing quite small enough to be Earth. Interesting. So what's going on? Okay, well, orbits of many of the known extrasolar planets, all right, look something like this. And notice that many of them are very close in, because here, I'll highlight it, or at least trace over it. Here is Earth's orbit, okay? And here are lots of other orbits of planets not in our own solar system. These are no more Mercury, Venus, Jupiter, none of that. Every one of these orange lines represents a known extrasolar planet around some other sun, not all around the same, or some other star, not all around the same star. Obviously, these are collected lots of data here. But notice there are so many that have smaller orbits than Earth. All right, and some of them have smaller orbits than Earth and are highly elliptical. Right, that's that eccentric. Okay, they have eccentric orbits. Okay, and there are certainly some that are further out. All right, we see that. All right, but many closer in. And actually, this graph only shows the ones that are closer in up to about maybe 1/3 of Earth's orbit, because if we wanted to zoom in on this region here, we'd have to actually have solid orange, because there's so many planets that exist in this really tight region right around their sun, all right, their star. So they'll point that out on the next slide, right? So planets orbiting with an orbit of less than 0.15 astronomical units, so less than 15% of Earth's average orbit, of their stars are called hot Jupiters. And they were called hot Jupiters if they're massive enough, right? So they wouldn't be necessarily called a hot Jupiter if they were only Neptune size, but if they have a mass similar to Jupiter's, we call them hot Jupiters, all right? And they're not even included in the previous figure, again, because they wouldn't fit, all right? But they're very numerous. They're very common, All right. So, and furthermore, another interesting point is stars with composition like our sun are much more likely to have planets. And so that's suggesting that, that stars of our size, of our sun size, create that dusty disk that is very, that is prone to planet formation. It's a good conditions for planet formation. And it turns out smaller stars, ones that are maybe half the size of our sun, also seem to have good conditions. But as we get up into more massive stars, we don't see many planets. Those hotter, brighter stars just don't seem to allow the dust to actually condense into planets. They probably sweep it away before it has a chance to. Sweep it away by their outpouring of energy, those hot stars. Now, some of these planets may actually be brown dwarfs, as I mentioned before. So we do find gas giants around around other stars in other solar systems that are so massive that they actually suggest that they are failed stars. Okay? All right, but probably not that common. So recently, a planet with a mass close to the mass of Earth has been discovered orbiting our closest neighboring star system, Alpha Centauri. So there's actually an Earth-sized planet around Alpha Centauri, but it is about 25 times closer to its parent star. Now, Alpha Centauri is less bright than the Sun, but still, that is too close to suggest that that could be a planet that supports life. It probably has conditions more like Mercury, even though it's a bigger version of Mercury. All right? And this figure shows Alpha Centauri, system to the left, where to find it, and an artist's conception of the planet shown there. But it's probably just a rocky, barren planet. But still very interesting that we have now finally confirmed that there are other planets with an Earth-like mass. And we found a few more, but not that many. All right? Why is that? So this figure shows two transiting super-Earths. All right, it's another category of planets in other solar systems that seem to be more common. All right, plus the 9 habitable exoplanets that we found as of the mid 2013. So now we found more than 9. I'm not sure what the current number is, right? But there's at least a couple dozen planets that fall into the habitable category. I'll come back to talking about what habitable means in a minute. All right, and we're comparing these sizes of these discovered planets to Earth and Neptune. All right, so here's a couple of particularly good candidates for being habitable planets, and you can see their relative size between Earth and Neptune. All right, this one is probably a gas giant and does not have a hard surface. This one might have a hard surface. These planets certainly here are most likely terrestrial, so they would be either Earth-like, Venus-like, Mercury-like, or something in between. And we can see that they actually are quite comparable to Earth's mass. All right, so I want to stress this point because although we saw in that previous graph that there's practically none in terms of planets that are discovered like Earth, and that's in comparison to the hundreds of Jupiter-sized and Neptune-sized planets that we have discovered around other stars, there's not literally none. We have discovered a few Earth-like planets. They're just rare. Well, the other planet systems discovered so far appear to be very different from ours. Hopefully that's become clear, right? Because we talked about that most of them don't seem to have Earth-sized planets, and most of them seem to have lots of large planets, some way bigger than Jupiter, those brown dwarfs, and many Jupiter-sized planets that have these incredibly tight orbits, really close to their star. Well, there's something here that's probably dominant, that what's probably happening, and that's a selection effect bias. Because those large planets, they're easier to detect. Think about how extrasolar planets are detected, right? Well, the large planets are, right, I'm gonna write this down again. Large planets are easier to detect, right? That's why we're finding so many of them. Not because necessarily they're the most common type of planet out there. It's just the only type that we have that we can actually clearly identify. All right. So we have that bias towards sampling, that means discovering those massive planets. Furthermore, we're going to find the ones that are close because if they're massive and close, they're going to tug a lot on their star. And that's going to make it very easily detectable Doppler effect wobble. And it easily detectable, if the orientation is right, eclipsing luminosity drop, right? Whereas low mass planets like Earth could hardly be detected, right? If we were aliens and we lived say 10 light years away from our solar system, our sun, and we looked at our solar system with our current technology, if those aliens had the same technology as us, they wouldn't be able to find Earth because Earth has an orbit that takes 365 days. So you'd have to wait 365 days to catch an eclipse, and that's if you're oriented just right. And it'd be a tiny, tiny drop in luminosity. And the wobble would just be a few centimeters per second. And so it'd be so hard to actually detect that Doppler effect wobble due to the motion of the star being pulled on by Earth's gravity, because we're so small compared to the sun. All right. So that's the idea. It's not because necessarily Earth-like planets are rare, they're just much harder to detect. All right, well, that's a little disappointing, isn't it? Because it doesn't really tell us if our solar system is rare or not. It just tells us what our bias is in terms of what we find. We tend to find massive planets that are close to their stars. But what is cool is that we're finding hot Jupiters, because we didn't know hot Jupiters exist because we don't have any in our own solar system. So that is a neat discovery in its own right. Even if we have a bias to finding hot Jupiters, the fact that they're out there is kind of cool. All right. So here's an example of a cold Jupiter, that's like our Jupiter, in another system. So actual data from a star system labeled in a quite poetic way, HD 154345, right? All right, so it's similar, its orbit is very similar to Jupiter's, right? This is truly a Jupiter clone, which is pretty neat to really find a planet that does the same thing. All right. So current theories include the possibility that Jupiter-like planets, the hot Jupiters, they migrate inward through friction with the solar nebula. So you have a planet that forms like our Jupiter formed, a giant planet, but over time it spirals inwards as it loses energy via friction until it eventually gets in to that tight, smaller than Mercury orbit that we see all those hot Jupiters have. And the reason we need a theory like this, and the reason you need a theory that has this friction with the solar nebula, is because we have no theory. There's no valid astronomical theory to suggest that gas planets could have formed where we currently see many of them, in that less than 0.15 astronomical unit orbit. Honestly, there's no one thinks that they form that way, because there's just no way for the gases to build up and to have that condensation of frozen hydrogen compounds that we're pretty sure leads to the formation of Jovian planets. It has to happen outside the frost line, and these hot Jupiters are well inside the frost line. So the migration really seems like it must be happening. And that idea of migration, of an inward migration of a Jupiter-sized planet, would also explain, and this is good because it kind of confirms, it would also explain all the eccentricity. Because remember how we mentioned that on average, the eccentricity of extrasolar planets is greater than the eccentricity of the average planet in our own solar system? Well, that could be because all these solar systems that have hot Jupiters, as Jupiter migrated inwards, it had gravitational interactions with other planets, causing their orbits to get a little out of whack, leaving them with more elliptical orbits than we see. So that does beg the question, why not here? Why did we not have migration of, say, Jupiter or Saturn inward to an orbit tighter than Mercury in our own solar system? Well, it may have just been due to some actual unusual attributes of our solar system. So maybe our solar system is a little unusual, but maybe it's not unusual because of Earth, even though we haven't found that many Earths, because again, the selection bias. Maybe it's just unusual because it doesn't have a hot Jupiter. Okay, so it's a different type of unusual. So a number of Earth-like planets have now been observed. Although due to detection difficulties, that's that aforementioned bias, most extrasolar planets still fall into that hot Jupiter category because those are by far the easiest to detect. All right, making other planetary systems look quite different from our own. So definitely, indeed, are we unusual? Yes, to some extent, because we don't have a hot Jupiter. Okay? But until we are able to observe much smaller planets at much larger distances, we can't say for sure if it's unusual that we have a Neptune, because it'd be so far very difficult to detect a Neptune distant planet, because remember how distant Neptune is from our own sun, or if a planet like Uranus even is common, right? So we just don't know if those are common or not, and we don't know if lots of planets like Venus and Earth and Mars are common either. Again, because they're so small, they're hard to detect, even though they're closer. All right, so we're left in it, with a unsatisfying answer here. Yes and no, right? So on the one hand, we're unusual because we don't have a hot Jupiter. On the other hand, we don't know if we're unusual by having planets like Earth, Neptune, and Uranus, because we may just not be discovering those types of planets, and planets like Earth, Neptune, and Uranus are common. But there's one last thing I haven't talked about, and that's, why don't we have a hot Jupiter? Because that does demand an explanation, doesn't it? Why not, right? Why don't we? I commented on here. Why not here? Why don't we have one? Well, Theories abound, the hypotheses abound, but perhaps our sun just went through a more energetic phase that pushed some of this solar nebula away during its protosun phase, allowing for less friction and thus no spiraling of planets like Jupiter and Saturn. All right, so maybe our sun was a little unusual and just burned a little extra hot or spun a little extra fast, produced some very energetic solar wind in the first 50 million years or so, pushed a lot of that solar nebula away, and that was all it took. But we definitely need to confirm that in maybe finding some other solar systems that don't have a hot Jupiter and do have planets like Earth and so on. But it just requires lots more detection, lots more high quality space-based telescopes. So the one thing we want to finish on is what the question we keep coming back to, and that's this idea of finding planets like Earth. Because we care because that could be our future home, or that could be the home of another alien like us, another species living in another solar system, doing things like us, living on a world with green continents and a blue sky and oceans like us. Well, that means we need to find planets that are Earth-like in size, right, as we saw here, but also Earth-like in their distance from their star, because that would make them habitable. And let's think about what we mean by habitable and the habitable zone. Well, this figure describes it, but let me first read what's going on here. Right? So the habitable zone is where there is a possibility of liquid water being present. That's it. You need liquid water on the surface. Now, you don't need to guarantee liquid water on the surface because the possibility requires that that planet has an atmosphere to protect the liquid water, but you at least need to have the possibility, okay? And the possibility of liquid water is a function of the mass of the parent star, right? That's the biggest thing. If you know the mass of the parent star, then you can find out where the habitable zone exists, okay? That's all you really need to know, because larger mass stars, they have a greater fusion rate, and so they push the habitable zone out. So note that the presence or absence of a greenhouse effect can affect the surface temperature of a planet considerably. And that's what I meant, and that's what I was stressing a moment ago when I said the possibility. Because again, being in the habitable zone doesn't guarantee liquid water. Case in point, let's look at the figure. All right, because if we look on the vertical axis, we have mass of the star, and the horizontal axis is just distance from the star. And the habitable zone is this green band right up the middle. It's basically a complicated function to figure out exactly why it goes like this. But when we look at our own sun and stars like our own sun that correspond to this horizontal line, and we look right at the planets in our own solar system, we see that Earth is right in the middle of the habitable zone, go figure. But we also see that Venus and Mars, especially Mars, are in the habitable zone. But neither of them do have liquid water, or at least in the case of Mars, very little liquid water. It might have some mud flows occasionally, seasonal mud flows. But again, that's because Mars doesn't have a good atmosphere. So Mars could have a lot more liquid water. All it would need is a decent atmosphere, but it doesn't have it. So that's the idea that, that possibility of liquid water, not guaranteed. But we certainly see that there are other planets that we've discovered in the habitable zones of their stars, but nothing in any star is bigger than our sun. Because even though a habitable zone does exist, it starts to become tighter because the sun becomes hotter. There's kind of a tighter range that would actually allow for a planet to exist there, and there also starts to be more radiation, and it's probably not the place to look. But the place to look for habitable planets, either for future colonization or for human-like aliens, then we want to look for planets like these. All right, including this one here, Kepler 69c, that not only is in the habitable zone, but is Earth-like with only a size of 1.7 times the Earth radii. All right, so pretty neat. But before you go rushing off thinking like, hey, we've discovered our future home, we just got to go head over to Kepler 69c, we got to remember the unfortunate reality that even the closest of these extrasolar planets would take hundreds of years, in some cases a few thousand years, for our fastest space probes to travel to. So yeah, getting there is not within our current technological constraints. But maybe in the future we'll discover a way to travel between the stars. As for now, we're just going to keep looking at the stars, looking at the planets around them, and talking about which ones might support life. But one thing we can do is we can train our radioscopes towards them and listen, because who knows, maybe we can discover someone talking on one of these other worlds. All right, so let's summarize our extrasolar planets. Well, condensation theory leads us to expect that other solar systems would be coplanar with planets orbiting in the same sense that our own solar system has. Coplanar means that the solar system builds up as a disk, right? The cloud collapses, it forms a disk, and then all the planets orbit on what was that disk. That's why we see in our own solar system all the planets orbit on almost exactly the ecliptic plane with only small deviations. All right? Random collisions should lead to irregular properties. We see lots of irregular properties in our own solar system. We should expect the same in other solar systems. Most extrasolar planets have been discovered through wobbling of parent stars. That Doppler technique is really the dominant and best technique that's still used, but we're always developing new ones. Obviously, the transit and the luminosity drop is important as well. There's been well more than 900 planets, extrasolar planets discovered. 20% of the systems and 33% of the candidates have multiple planets per system. So it seems like having multiple planets is not unusual. So in that respect, we have a typical solar system. And we found about 20 Earths or super Earths so far in the habitable zone. So we already have lots of real like potential Earth twins out there. And we don't yet have enough information to tell us how unusual our system is. But hopefully we will in the future. Well, I hope this lecture on extrasolar planets has been both interesting and informative. Thank you so much for watching.